talk about limited contention protocols, but not nearly as exciting as he was. So anyways, contention is preferable under conditions of light load due to its low delay, and this is an example of that is pure and slotted aloha, since collisions are rare. And collision-free protocols are favorable at high load because of the improved channel efficiency since overheads are fixed. What limited contention protocols do is they attempt to combine the best properties of contention and collision-free protocols. This is showing the success rate of contention channels, and the y-axis is supposed to be the success rate. I chopped off the caption or whatever. But you can see that any more than 5 channels and it pretty much asymptotes off and everybody's pretty much competing and not having a high success rate. So that's only favorable when there are a low number of channels competing. So what limited contention protocols do is stations get divided into groups. Only members of group 0 can compete for slot 0. If successful, the member acquires the channel and transmits its frame, and if not, the members of group 1 compete for slot 1. And if that loses you, then there's a visual later and you'll understand it then. How do you assign stations to slots? As more stations are assigned to the same slot, the probability of collisions grows, but the length of the bitmap scan needed to give everyone a chance shrinks. And special cases are each group has 1 member. There's no chance for a collision because there's just 1 person. So the binary countdown is an example of that. 2 stations per group is a little chance of collision. And the limiting case is a single group containing all stations, which is what slotted aloha does. So what we need to do is we need to have a method that assigns stations to slots dynamically with many stations per slot, or even just 1 station per slot when the load is high. And you do that with a binary tree. So an example is that stations at the bottom, C, E, F, and H are competing for slot 0. And what you would do is go through the binary tree with a depth search. And if you don't remember how that works, you go from 1 to 2 to 4 to A to B to 5 to C to D to 3 to 6 to E to F, 7 G to H. Anyways, C, E, F, and H are all competing for slot 0. So you drop from 1 to 2, from 2 to... I didn't touch that. So you drop from 2 to 4, and A and B aren't competing, so you go to 5, there's C. C gets slot 0. So then your new group is E, F, and H, and they're competing for slot 1. D doesn't want the slot, so you go to 3, drop down to 6. E and F are both under 6, so you have to drop to E. E gets slot 1. Your new group is F and H. F is right there, it gets slot 2. And then you go to 7, and H is under 7, so you give that the slot. And that's how you do it the slow way, manually. The algorithm behind it is a lot more complex, and if G and H were competing and they're the only ones competing, as soon as it goes to 2 and the search for 2 comes up empty, it knows that it has to be under 3, so it skips straight to 6. And it also looks at the number of people, or number of stations, and determines where it needs to start searching the tree. So it doesn't necessarily have to start at 1, it can start lower. And that's just how smart the algorithm is nowadays, but there's no sense in throwing that out there because it's got like a logarithm and an exponent, all kinds of stuff in it. And that's limited contention.